Και τώρα ξεκινάμε με την πρώτη ενότητα, Session 1, Decarbonization and Green Pathway in Shipping. Καλείται ο Chairman, Dr. Δημήτρης Οφαλιός, Chairman of Intercargo, και πλέον επίτιμος διδάκτορας του Τμήματος Ναυτιλίας και Επιχειρηματικών Υπηρεσιών του Πανεπιστημίου Αιγαίου. Επίσης, μαζί του οι ομιλητές, κύριος Πάνος Ζαχαριάδης, Σταμάτης Φραδέλος, Μπίλ Σταματόπουλος, ο κύριος Λίλας, επίκουρος καθηγητής του Τμήματος Ναυτιλίας, και ο κύριος Λυρίδης από το Εθνικό Μετσόβιο Πολυτεχνείο.
Good morning, esteemed guests, ladies and gentlemen, dear students. Welcome to the first HIOS Shipping Summit. I hope the first of many. A very warm thanks to the organizers, to the university, and to the hardworking technicians who make this all possible. We'll carry out this panel predominantly in English. We hope to have a Q&A session after the presentations from our panelists, and the Q&A session, of course, can be in both languages. Now, we're gathered here in Chios, a shipping and seafaring island with hundreds of years of experience. I will also ask, or not ask, I will also suggest that if you would like to see a little bit more about Chios's history in shipping and seafaring, the Chios Nautical Museum is worth a visit. Chios Shipping's strive for efficiency is deep-rooted and fundamental. Chian ship owners and Chian seafarers have fought hard for, I would say, hundreds of years, but more recently in the fuel oil era, they have fought very, very hard to minimize, to reduce every single drop of fuel, of lubricants, of chemicals that are used on board each vessel. The efficient vessel is the vessel that gets the business. And Chian ship owners and Chian seafarers have understood this many, many, many years ago. They have been amongst the pioneers of new technologies and of new ways of improving energy efficiency. However, in this new era of decarbonization, energy efficiency alone will not allow us to reach our decarbonization goals. And in order to reach these goals, we need safe, alternative, low carbon or zero carbon fuels. We have therefore gathered today an excellent group of panelists. I think many of them are known to you all. Just for the sake of those that have not read the conference program, Mr. Panos Zachariadis, Fleet Technical Director of Atlantic Bulk Carriers, Mr. Stamatis Fradelos, Vice President of Regulatory Affairs of the American Bureau of Shipping, Mr. Bill Stamatopoulos Vasilis, Director of Verifuel Global Business Development in the Bureau Veritas Group. And we're also very privileged to have Assistant Professor Dimitris Liridis from the National Technical University of Athens, and very importantly, Professor Thodoros Lilas from the University of Aegean here in Chios. So we will start off by asking them to each make a short presentation. We will take the presentations one after the other in order to be mindful of time. And then at the end of the presentations, of all the presentations, we will take some questions and answers gladly from the audience. Thank you. And I think that we're going to start with Stamatis, who's going to give us some idea of the regulatory framework that we find ourselves in. Thank you.
Καλημέρα. Ευχαριστώ πολύ. Ευχαριστώ για την πρόσκληση. Είναι μεγάλη χαρά και τιμή μου να είμαι στο όμορφο νησί σας μεταξύ γνωστών και φίλων και χαίρομαι ιδιαίτερα που βλέπω και φοιτητές στο ακροατήριο, γιατί όπως αναφέρθηκε εχθές το απόγευμα ο κ. Φαφαλιός, το ταξίδι της απαθρακοποίησης έχει ήδη ξεκινήσει. Θα χρειαστούμε περίπου σχεδόν 30 χρόνια, οπότε εσείς θα είστε οι επόμενοι που θα αναλάβετε τα ενία. Αυτή είναι μια δουλειά για να πετύχουμε, η οποία χρειάζεται ομαδική προσπάθεια. Θα γυρίσω στα αγγλικά. I don't know. I can change the slides here. So it was I promised to Mr. Fafaghios to stay within 6-7 minutes. Of course, it is very difficult because now we have a tsunami of new regulations. And so I will try to keep on just on high level, and later on we may be able to discuss in detail. So Mr. Fafaghios yesterday evening, he mentioned about the 2023 revised strategy of IMO, and you can see there the transaction line. We need to be carbon neutral by 2050, and you see also the checkpoints in 2030, 2040. The first one in 2030, you see there is a target about carbon intensity, reduce our carbon intensity by 40% compared to the year 2008. And we believe that we are almost there because we have much more efficient ships. So our efficiency has been improved, and this has been approved through the latest study, the GHG greenhouse gas study. And we believe when we have the next study issued, published, we will be able to almost achieve this target. Through the EDI, we have the introduction of new ships in 2013, more efficient ships. We have larger ships, and of course, we have reduced our speed. But what is important to mention is that the absolute, although we are improving our efficiency, the absolute emissions still increasing. I mean, this was the result of the last study. So the other target about the reduction of the absolute emission is quite challenging. This is the challenging part for shipping. And as you can see, there are targets. So we need to achieve 20% reduction on absolute emissions by 2030. And then you see the next target. This is the most important challenging target for us, about 70% in 2040. So we have the strategy, and let's see how we are going to achieve this. I'm sure you are familiar with the midterm, the short-term measures, CXI and CII, and the EDI that we introduced back in 2013, but these are not considered sufficient. And IMO is moving on additional measures. Unfortunately, this is not working. Okay. So yes. So what IMO wants to do is to provide incentives. It has been recognized that this is a barrier. I mean, why ship owners to invest additional 10 million, for example, for a ship that will be able to burn methanol or LNG or LPG or ammonia if there is no payback, short payback, reasonable payback period. So what IMO is going to do is to provide incentives to the early movers, right? So actually, they're going to reduce the price difference between the new fuels, the low carbon fuels and the conventional fuels. So there are some proposals, those that you can see on the circle, which actually aim to raise revenue and to support this decarbonization by investing on new ships, by funding the development of low carbon fuels, on research and development, supporting developing countries. So apart of these mechanisms, we have also in the middle, you see the GHG fuel standard. This is a different concept. This is a technical measure. With this standard, the GFS, actually IMO is going to set some limits on the carbon intensity of the fuels we are using. So in a similar way we had in the past with the sulfur content, that ships will need to reduce the sulfur content of the fuels they use. We have a similar concept now regarding the carbon content. So you can see here what will be the additional daily cost depending on the different proposals and the carbon pricing. And imagine if we have a price those for let's say the ICS proposal, which is $12.5 per ton of CO2, this will raise around $10 billion per year to invest on this decarbonization effort. Apart this, there was also mentioned by Mr. Fafalios about the regional measures, and you know, operators have now a headache how they can comply with the EU ETS that is starting 1st January 2024, which is a similar mechanism, a cap on CO2 emissions. And the FuelEU Maritime Regulation, which is starting 1 year later in 2025, this is same concept with the GFS I mentioned previously. And here you can see what will be the additional daily cost regarding the EU ETS. And you will see in 2024, we have 40% cost. In 2025, 70%, and from 2026, we'll have to pay for 100% of our emissions. Of course, for voyages in and out in Europe, we have to count 50% of that emissions. And here you can see also it's the same slide. Yes, so here it's not the EU ETS, it's the FuelEU Maritime Regulation cost. And you can see what is the daily cost increasing as the limits of the fuel, on the carbon intensity of the fuels you have to use falls every 5 years. So what you can see is from the year 2035, the FuelEU ETS cost is becoming higher than the EU ETS cost. And this concludes my presentation. I hope I stayed within the 5 minutes.
Thank you, Stamati. And whilst Panos gets ready for his presentation, I just also wanted to add that our panelists combine many capabilities in many disciplines, from classification, from fuels, from academia, and as Panos is going to talk us now from real real world experience of decarbonization in practice. Thank you, and over to Panos.
Καλημέρα σας και ευχαριστώ πολύ για την τιμή που μου κάνατε να ξαναδώ τυχείο από τότε που ήμουν παιδάκι έχω να έρθω, οπότε είναι η τέλεια ευκαιρία. Λοιπόν, ο πρόεδρος του πάνελ μου ζήτησε να μιλήσω για το τι μπορούμε να κάνουμε στα υπάρχοντα πλοία, όχι για τα new buildings. Οπότε θα συνεχίσω τώρα στα αγγλικά. Energy efficiency for existing ships. Και εδώ βλέπουμε πόσα είναι τα existing ships. Βλέπετε ότι τα tankers είναι 29%, containers είναι 13% και μπαλκάρια 43%. Από ένα σύνολο πλοίων γύρω στις 60.000 το υπολογίζουμε. Και ας δούμε τώρα τι emissions έχουν αυτά τα existing ships. Δεν ξέρω αν θα έπρεπε να συνεχίσω στα αγγλικά. Καλύτερα μήπως για το YouTube. Better continue in English. So, we have the existing ships and we have the emission division of those existing ships in CO2. And you'll note that container ships, being 13% only of the ships in the oceans, emit most of the CO2. They emit 30%. Valkyries, even though they are 45%, they emit only 27.5% of the CO2. So you would think regulations aimed at reducing CO2 emissions should be directed primarily towards container ships, but they don't. I'm sorry to say that big lobbies were able to leave container ships pretty much unaffected as far as EEDI and EEXI and so forth, unfortunately. So just another nice pictorial I found. The energy for 1 day of a container ship is the same as the energy you need for 50,000 homes. Now, one of the problems that we have in trying to improve the efficiency of ships is that we don't have a good way to measure the efficiency of ships. And unfortunately, I have to say that those indices that we use, ZOI, CII, EEDI, I'm going to be blunt, they're nonsense. Okay, they simply do not give the efficiency of a ship. I'm not going to go into the details why they don't, but you can look it up or we can discuss it later. So what can you do to improve the efficiency of existing ships? This is a pictorial that pretty much covers everything you can do on an existing ships. The ones that I have mentioned as O is operational. This is what you can do easily by fixing the operation of existing ships. The D or T is design or technical measures. So you have operational measures, design or technical measures. For example, reducing the maximum power with EEXI of the main engine is a technical measure, but it can also be a design measure right from the shipyard. If you look at operational measures, the most effective one, which can give you up to 75% reduction in CO2 emissions, is slowing down, reducing your speed. That's the most effective thing you can do on an existing ship. But you can do other things too. There are some cost-effective things you can do, retrofits, energy-saving devices. Cost-effective, in other words, they don't cost much, but they give you very small reductions, like wake equalizing ducts or small propellers in front of the big propeller. Those things give you 1, 2, 3, 4% reduction in fuel consumption, and therefore the same reduction in CO2 emissions. Also lately, we see that more and more companies, and that's relevant for CII, are using monitoring software. And I have used them, and I can tell you that they can give you a good amount. Some of them use AI. They can give you a good amount of fuel reductions, perhaps up to 10%. So that's something very cost-effective. They can help the captain plan the best course, taking into account the weather ahead. And I'm not talking about bypassing the weather totally. I'm talking about getting into the bad weather up to Beaufort 8 or 9, reducing speed during that time, and then increasing speed after he leaves the bad weather. So you can have the charter party speed satisfied, but at the same time, reduce your fuel consumption compared to a normal course that you would take before these tools were available. Also, lately we see some non-cost-effective solutions, which unfortunately practically still would give you small reductions. And this is like fixed sails, flattener rotors, air lubrication. The makers advertise up to, and you can put a number. I mean, I have seen up to 30% fuel reductions. But then when I ask people who have actually put them what the reduction is, it's around 4% reduction for all those things, and they cost millions. But of course, some companies, they don't see the cost effectiveness only. There is some companies that say, we don't see it this way. We are paying money to reduce our emissions and be more green. Batteries, unfortunately, are not suitable for large ships and large distances. Just to give you an idea, if you want to move a container ship with batteries from Asia to Europe, you'll need 100,000 tons of batteries to be on board just to make the trip at the most fuel efficient speed. Other near-term possible solutions that we're working right now is carbon capture, and one of the next speakers is going to talk extensively about that. Right now, it's very expensive, and the science is not fixed yet, but we're working on it. Let's see how it goes. One huge thing that could give us 40% reduction is to get on board the chain of transportation, the ports. And this is called virtual arrival. If theoretically all the ports in the world were applying virtual arrival, we could easily reduce CO2 emissions from shipping by 40%. And there are studies for that. What virtual arrival is instead of a ship going full speed to arrive at the port and get in line for the berth, and the berth is busy. So you speed up only to get in queue before another ship to berth whenever the berth is free. You communicate to the port, you say, if I come full speed, my arrival is going to be such a date and time. If you accept this and you put me down in the books for that arrival time, then I can slow down and arrive whenever the berth is going to be free. That's a huge thing. Instead of having anchorages full of ships waiting to come into the port, and as I said before, slowing down is the best way to have large CO2 reductions. Of course, another thing you can do is switch to green fuels. You can use drop-in fuels such as biofuels, and Mrs. Stamatopoulos is going to talk to us about that. If you're talking about the other green fuels, eventually you can use green methanol in existing ships. Methanol is the only fuel that you can retrofit an existing ship to burn. You cannot retrofit an existing ship to burn ammonia, for example. And that's another thing that bothers me. There is a push because methanol can use all the existing infrastructure, the existing bunker barges, bunker facilities, the existing ship engines. Easily, you can retrofit them to burn methanol, but not for hydrogen or ammonia. Hydrogen or ammonia, you have to throw away all the existing infrastructure and all the existing ships and build new ones that can burn those fuels. And finally, a word about the possibility of nuclear energy. It could become as a retrofit, and we're not talking about the nuclear energy we all know. We're talking about the new fourth generation nuclear energy that they are working on right now. There is 6 large projects worldwide. It's molten salt reactors. Extremely safe because they don't need active cooling. They don't need any cooling. So there is no possibility of meltdown. And of course, the fuel is already molten. So meltdown is not an issue. And eventually, a prototype is being built right now. They're saying it might be workable by 2027. If this new technology works, it might be a solution both as a ship engine, because it's very small, and as a way to produce green hydrogen. And that's another solution, hybrid. Thank you very much.
Panos, thank you very much. Very insightful. And now Bill will talk to us about biofuels, which are, I think, very important on our long journey towards decarbonization. Thank you.
Καλημέρα, σας ευχαριστώ πολύ για την πρόσκληση και την τιμή να βρίσκομαι πρώτη φορά στη Χίο. Εγώ δεν είχα έρθει ούτε σαν παιδάκι, σαν τον κύριο Χαχαριάδη, και θα σας μιλήσω για τα βιοκαύσιμα για ένα very short term period, γιατί αν αναλογιστούμε ότι υπάρχει και το LNG και το biofuel είναι τα μοναδικά καύσιμα που έχουμε μέχρι το 2030. So, it was the ISO 217-2017 latest edition that opened the door to biofuels. Before that, the fuel was supposed to be purely a petroleum hydrocarbon, but the latest edition included synthetic or renewable sources. And when it comes to our industry, predominantly we're talking about FAME, the fatty acid methyl esters, and the hydrotreated vegetable oils, but especially this one, the renewable diesel, comes with a price tag. And the very first time we started discussing about biofuels was towards the end of 2018. Then we started working on the first trial, and we take pride because we were the very first ones to be involved. The trial took place in early 2019 with a very conservative mixture. It was marine gas oil and UCOM, that is the methyl ester of used cooking oil. You can have used cooking oil or the methyl ester used cooking oil, that is the most appropriate component. Relevant to a discussion that I had with Dr. Dimitris and French fries and used cooking oil. So it went very well. No side effects, business as usual. And then we started with different formulations and recipes. The very second trial was like 250 metric tons in Rotterdam. And the owner said, I will try it. And the vessel was supposed to go to dry dock. So it was a little bit on the safe side. Then we started moving to more exotic blends. This is a B100. You don't have any fossil fuel. It's 100% renewable. It resembles a marine distillate oil, like marine gas oil or marine diesel oil, and it comes with a very, very low carbon factor. Singapore, that is the biggest bunkering port, started last year supplying B24. This is by far the most popular grade in Singapore. So what you are getting is 24% of used cooking oil, the methyl ester of used cooking oil, and VLSFO. And one of the reasons that B24 is so popular is that there is a MARPOL Annex 1 requirement that the seagoing, the bunker barges, may carry up to B25. And above that, you need the chemical tankers. This is not the case in the Amsterdam, Rotterdam, Antwerp area because the local barges are classified as river barges. Remember that following an Ajax submission to IMO to facilitate the uptake of biofuels, the NOx issue has been resolved to a very big degree. Any biofuel with up to B30 is considered to be a petroleum hydrocarbon. For B31 and higher, unless critical engine settings are required by the maker to maintain the NOx technical file, is still business as usual. The MEPC 80 interim guidelines assisted in evaluating the carbon factor because so far we were using different techniques basis the IMO guideline. And the blue thing that you can see is the famous proof of sustainability. We call it POS. We are very familiar. We go to a tavern and they ask, you will pay with a credit card or with a POS, but this is proof of sustainability. So you are getting this together with a bunker delivery note every time you will buy a biofuel, especially after the 1st of October 2023. And then the carbon factor is derived by the lower calorific value and the energy intensity of the product as given by the supplier. Just to see quickly how it works for the IMO purposes, let's say that we got a B25 and the certified POS by ISCC shows an energy of 20 and a low calorific value of 37 megajoules per kilogram for the biocomponent. And for the VLSFO, for the time being, we are using the IMO guidelines. So doing the maths, the B25 comes with a carbon factor of 2.56 to be compared with what we are using today in the traditional fuels like 311, 315 or 320 for the distillate. So this is the reduction you can get. But of course, if you go to a very expensive product like the B100, the corresponding carbon factor is 0.75. In the case of a tanker that is emitting 22,000 metric tons of CO2, that is 12% of distillates and 88% of heavy fuel oil, if we continue as is and we don't make any changes, so we continue with the traditional fuels, that means that this vessel will be 2 years on C, then 4 years on D, and the last 3 years till 2030 to E. And we have two quick scenarios. The first one is that we start adding B100 from 2% up to 38. And the second scenario is that we are adding a B25, that is a less expensive biocomponent, from 5% to 100%. So what will happen with this scenario is that by playing with the drop-in of B100, the vessel will stay on C till 2030, while with the B25, it will be 6 years on C, 2 years on D, and the last year on E. In case a company wants to go for the very first trial, what we need to have is a risk assessment, a fuel utilization plan, to carefully study the certificate of quality of the final product, to know if it's FAME-based, for how long it was stored ashore before we get it on board. We need a proof of sustainability, and then we typically communicate with the engine makers, we involve class society, and we inform flag state. We don't ask for the permission any longer in terms of NOx. A special testing slate can be used for the biofuels. And if you go to a fuel supplier today and you ask for biofuels, the first thing they will ask you is, what about the volume? I need the commitment of volume because I need to secure the feedstocks. So in this respect, the liners have an advantage because they know on forehand the ports and the volumes. But it's interesting to know that, to note actually, the uptake 2021, 67,000 metric tons of biofuel sold. And in last year, we had close to 1 million metric tons of biofuels. So there is a high momentum. There will be an availability issue. The fuel supplier says that the waste and the residues can be up to 40 million, but this is not all for the shipping industry. We have to compete with aviation. We have to compete with national mandates for transportation for road diesel. But the concluding remark is that it will never be the fuel of the future, but probably is the best stepping stone to decarbonization. Thank you very much.
Thank you very much, Bill. Very, very insightful. Now maybe Professor Lyridis can tell us about another very promising technology carbon capture. I will start with carbon capture and then develop, I guess, to carbon capture and storage. So over to Professor. Thank you.
Hey, good morning, everybody. It's a great honor to be here. I've been here since the BCE years before COVID era. So it's a great honor. Congratulations also to Mr. Chairman. So without spending any more time, I will speak a little bit quickly about carbon capture in shipping. I have a lot of transparencies. They will be available to the public. If needed, we don't go through all of these because they're a lot. So about the environmental challenges, it has already been discussed, a lot of regulations that need to somehow lead to shipping decarbonization. And let's talk about, change this, about carbon capture. There are basically three ways to use carbon capture in shipping and onshore, of course. It's pre-combustion, during combustion, oxy-fuel combustion capture, and post-combustion capture. I have a very analytic way how it works. In pre-combustion, you essentially steam reform the fuel before using it as a fuel. That needs air and water vapor. You steam reform it, you separate CO2 from hydrogen, and you use hydrogen as fuel, and then you store CO2. This is the pre-combustion phase. During the combustion, you use a very rich in oxygen mixture into the combustion chamber. You have to first separate nitrogen from oxygen, use oxygen in the combustion chamber, and then after the combustion, you just use the condensation to get out the water and use the CO2 in a storage place, somewhere on board. And the third way can be done technically in different technologies: membrane absorption, adsorption, multi-phase absorption, chemical looping combination, calcium looping, and a cryogenic way. There are a lot of technologies. Only one is can be applied most probably today. So in this way, you have first the normal combustion in the engine, and then you have the exhaust gas that goes through some separation from CO2. You keep the other gases and you store the CO2. Of all the technologies, I have opted to see a little bit more in detail how the most promising one for the time being works. In this case, you have the exhaust that goes into the engine. Then after the combustion, you take all the exhaust gas in an area where you have to cool it down. You put it in a place that is called a stripper or absorber. There you use amines, chemicals, that take CO2 out of the exhaust gas. This is then that goes into the, I don't have a pointer here. I do have a pointer. Yes. And it goes to this chamber where you separate the CO2 from the amines. The amines go back for reuse, and the CO2 goes to a place where you keep it. It's a pure CO2. So this is how it works. So these are the major technologies. I will not spend a lot more time on this, as this is an overview. The major problem is that these are all very expensive technologies, and most of the technologies are not mature enough. This table shows that of all the technologies, the most easily applicable is the amines, and this is where most of the research is done today, because all the others are either technically very difficult, or they have other problems with the cleanliness of CO2, the purity. Even cryogenic separation has problems. So the only available technology today is chemical absorption. Of course, we must know that carbon capture is a little bit like a Ponzi scheme. Since it is very expensive today, you spend a lot more energy in capturing CO2 than the actual CO2 that you capture. This has to be addressed. Another important point is that carbon capture cannot operate on its own. You need to have a whole supply chain where you take the CO2 from the ship and onshore, not only from ships, because it's not sustainable only from ships. You have to transport it somewhere and store it, or use it in some other way. But uses of CO2 are not so extensive. So the major problem is to store it some way, all the underground storage is one solution. There are, I think, 20 or 22 such sites in the EU, but you have to organize the entire supply chain, collecting CO2 from energy savoring industries like the cement industry, the paper industry. You have to drive it to hubs like a large port. You have to also take the CO2 stored on board ships there, and then you need to organize the supply chain with the ship to the end case. Here are some of the examples for places where CO2 capture has been applied. There are three very good cases. One is in Holland, one is in Norway, where you also have underground storage, and Switzerland has many places where they collect CO2, and they have also built a pipeline for transporting it. What is very important to know is that CO2 has quite some cost in its application. It's very expensive. You can see it on the left graph, where you see how expensive carbon capture can become. And studies show that it is only viable if the payback time is less than 5 years. After that, it appears that there will be it's assumed that there will be other fuels available, and in which case the people who will make the investment on CCS will not be able to take back to profit from their investment. So it's a big issue to be discussed. This is all for your consideration. I think carbon capture is one technology that can be used immediately. It's very expensive still. Maybe some research will drop down its cost, but it's still a very expensive technology, and it is only a temporary measure, but it is one technology that can give life to fuels like LNG or methanol that are not green yet. But we have to calculate always the life cycle cost, and the shipping community, I think, should press a lot towards the calculation of the life cycle cost of all these technologies, because sometimes the entire cost of capturing CO2 or avoiding the use of CO2 are more expensive or more carbon generating than the actual use. So this is very important. Thank you very much.
Our panelists have been very good on timekeeping. We have to give them an extra round of applause, please. Now, Professor Lilas will maintain our theme of decarbonization, but in a slightly different context. And we look forward to his presentation on floating, on energy decarbonization on floating platforms. Thank you.
Καλημέρα σας και από μένα. Καλώς ήρθατε στη Χίο. Είμαι μέλος του Εργαστηρίου Πληροφορικής Νέων Τεχνολογιών στην ναυτιλία και στην νησιωτική ανάπτυξη. Είναι διευθυντής ο κ. Νικητάκος, καθηγητής, και έχουμε και εξέχοντες καθηγητές στο εργαστήριο που θα ακούσετε και ομιλίες τους στη συνέχεια. Όπως είπατε, θα είναι λίγο διαφορετική ομιλία μου. Σαν μηχανικός που είμαι, έχω κάνει αρκετά έργα που σχετίζονται με την παρατήρηση, παρακολούθηση των λειτουργιών και μετά στη συνέχεια αναλύουμε το πρόβλημα και βελτιώνουμε σημαντικά, όπως αναφέρθηκε και προηγουμένως. Αυτή η διαδικασία μπορεί να μειώσει σημαντικά την κατανάλωση και αντίστοιχα να έχουμε βελτίωση στην αποδοτικότητα. Μερικές φορές όμως σκεφτόμαστε και να κάνουμε κάτι από την αρχή. Οπότε ξεκινήσαμε από αρχικές ιδέες σε πρώιμο στάδιο, πολλά χρόνια πριν. Οπότε ένας καλός δείκτης είναι το Technology Readiness Level που ξεκίνησε από την NASA και το υιοθέτησε και η Ευρωπαϊκή Ένωση στα ερευνητικά προγράμματα. Οπότε σε αυτό προχωρήσαμε αρκετά καλά, πιστεύω, ξεκινώντας από ιδέες με πλωτά συστήματα που μπορούν να δώσουν λύσεις. Βέβαια, για να έχεις κάτι επιτυχημένο είναι απαραίτητη και αντίστοιχη συμμετοχή της κοινότητας, αν υπάρχουν οι αντίστοιχες υποδομές και αν μπορούν να γίνουν και αντίστοιχες επενδύσεις, ώστε όλα αυτά να προοδεύσουν. Σαν ηλεκτρολόγος μηχανικός κατευθύνομαι περισσότερο προς τα ηλεκτρικά δίκτυα, αλλά θέλω και τα αυτόνομα συστήματα που λειτουργούν μόνα τους. Οπότε εδώ βλέπουμε ένα πλάνο που αξιοποιούνται σημαντικές υποδομές που έχουν γίνει ήδη, όπως είναι ανεμογεννήτριες, δίκτυα ανεμογεννητριών, αν αυτά μπορούν να δώσουν λύσεις και στην ναυτιλία. Αυτό που βλέπω έτσι σαν πιο άμεσο είναι ότι η ηλεκτροπρόωση θα επεκταθεί στο μέλλον. Σε συνδυασμό με υβριδικά συστήματα με μπαταρίες μπορεί να έχουμε και εξοικονόμηση ενέργειας και ευελιξία, αλλά και σημαντική αξιοπιστία. Παλιότερα αυτά τα συστήματα θεωρούνταν ακριβά και δύσχρηστα, αλλά πλέον έχουν μειωθεί αρκετά τα κόστη των ηλεκτρονικών και η διαχείριση των συστημάτων αυτών είναι αρκετά πιο εύκολη. Και στο μέλλον βλέπουμε, όπως είπαν, τα συνθετικά καύσιμα που μπορούν να χρησιμοποιηθούν όπως είναι στην πιο απλή μορφή με την ηλεκτρόλυση στο υδρογόνο, αλλά και με πιο σύνθετες διεργασίες, να συνδυαστούν με το διοξίδιο και να έχουμε καύσιμα όπως η μεθανόλ, η hydrogen και η LNG. Επίσης, αυτό που βλέπω σαν πιο δύσκολο και σημαντικό πρόβλημα και για την υγεία των ανθρώπων είναι οι εκπομπές των ρήπων κοντά στις ακτές και στα λιμάνια. Οπότε εκεί, αν μπορούμε όπως είπαμε, τα υβριδικά συστήματα να μην έχουμε καθόλου ρήπους, εκεί δεν έχουμε κανένα πρόβλημα για τους ανθρώπους και την υγεία των ανθρώπων. Και μια λύση που δεν ξέρω αν θα προχωρήσει, φυσικά όπως προχώρησε και στη ακτή, είναι το εικονικό net metering, δηλαδή αν επενδύσουν ναυτιλιακές εταιρείες σε ανανεώσιμες πηγές σε άλλα μέρη, ώστε να μειωθεί εκεί οι εκπομπές διοξιδίου του άνθρακα και αυτές να συμψηφιστούν με κάποιο τρόπο και τελικά, αφού δεν θα φτάσουν στην ατμόσφαιρα αυτές οι εκπομπές, να μπορούν να υπάρχει κάποιο όφελος. Εδώ βλέπουμε υπάρχει και μια τάση στα λιμάνια, εκτός από όλες τις άλλες δραστηριότητες, να γίνουν και ενεργειακοί κόμβοι στην ηλεκτρική ενέργεια. Έτσι, εκτός από ανεμογεννήτριες που τοποθετούνται στα λιμάνια, ας πούμε, το λιμάνι του Νόρτερ αναλαμβάνει και τη διαχείριση αιωλικών πάρκων στη θάλασσα, ώστε να αξιοποιήσει και την ενέργεια που παράγεται στο θαλάσσιο χώρο. Βλέπουμε εδώ δυνατότητες που παρέχονται με το cold ironing, με την τροφοδοσία των πλοίων στα λιμάνια, ώστε να μην έχουμε καθόλου ρήπους όταν βρίσκονται στα λιμάνια. Επίσης, υπάρχουν φιλόδοξα σχέδια που αναπτύσσονται σιγά-σιγά, οπότε δημιουργούνται υποδομές στο θαλάσσιο χώρο, συνδέονται μεταξύ τους τα αιωλικά πάρκα, άρα έχουμε ηλεκτρικά δίκτυα μεγάλων αποστάσεων που συνδέουν μεταξύ τους τις χώρες. Επίσης, βλέπουμε ότι η διαθέσιμη πόρη στη θάλασσα είναι ιδιαίτερα υψηλή, άρα βλέπουμε ότι έχουμε πολύ ισχυρό αιωλικό δυναμικό στη θάλασσα και όσο απομακρυνόμαστε στις ακτές και πηγαίνουμε σε μεγαλύτερα βάθη, υπάρχουν δυνατότητες να αξιοποιήσουμε την ενέργεια με δυνατότητες πολλαπλάσεις από την κατανάλωση που έχουμε σε μεγάλα ενεργοβόρα κράτη όπως και οι Ηνωμένες Πολιτείες και η Ευρωπαϊκή Ένωση. Έχουμε και στην Ελλάδα σημαντικό αιωλικό δυναμικό στο Αιγαίο και γύρω από την Κρήτη. Επίσης, βλέπουμε ότι αυτές οι κατασκευές, ενώ παλιότερα θεωρούνταν οι ανεμογεννήτριες κάτι μικρό, τώρα πλέον έχουν γίνει μεγάλες. Χρειαζόμαστε και ειδικά πλοία για να τις μεταφέρουμε. Εδώ βλέπετε πάνω δεξιά μια μεγάλη πλωτή ανεμογεννήτρια, είναι της τάξης των 6 ΜΒ, χρησιμοποιεί πολύ μεγάλους γερανούς για την τοποθέτησή της, όπως εκτείνεται πάνω περίπου 100 μέτρα από τη βάση της και η βάση της είναι περίπου πάνω από 100 μέτρα, πηγαίνει προς το βυθό, είναι πλωτή. Αριστερά βλέπουμε μια πολύ μεγαλύτερη ανεμογεννήτρια που είναι 15 ΜΒ και μόνο το φτερό της είναι 130 μέτρα. Άρα έχουμε τεράστιες κατασκευές που είναι συγκρίσιμες με τα πλοία και αυτό μπορεί να δίνει σημαντικές δουλειές στα ναυπηγεία. Μπορούν να κατασκευάσουν αντίστοιχες κατασκευές και επίσης και στα πλοία που χρειάζονται για την υλοποίηση αυτών των έργων. Στον τομέα αυτό, όταν ξεκινήσαμε στην έρευνα και κατασκευάσαμε την ιδρυάδα που βλέπετε αριστερά, δεν υπήρχαν άλλες ανεμογεννήτριες σε πλωτές κατασκευές σε αυτή την κλίμακα. Τώρα υπάρχει μεγάλο ενδιαφέρον, προτείνονται συνέχεια καινούριες κατασκευές και τελευταία ακούστηκε ότι και ο Τέσλα θα επενδύσει σε αυτή την κατεύθυνση για να έχουμε πολύ μεγάλες ανεμογεννήτριες που να ξεπεράσουν πολύ τις κατασκευές που έχουμε μέχρι τώρα, τα 15 ΜΒ και ελπίζουν να φτάσουν στα 50 ΜΒ. Ενέργεια που είναι συγκρίσιμη με ένα μεγάλο πλοίο που χρειάζεται ένα μεγάλο πλοίο. Τώρα, αυτό που σκεφτήκαμε και να προχωρήσουμε πέρα από την κατασκευή μιας πλωτής ανεμογεννήτριας ήταν, αφού υπάρχει αυτή η υποδομή που είναι αρκετά ακριβή, να συνδυάσουμε και άλλες τεχνολογίες πάνω στην πλωτή πλατφόρμα, να αξιοποιήσουμε ανανεώσιμες πηγές ενέργειας εκτός από την αιωλική ενέργεια, τα φωτοβολταϊκά και την κυματική ενέργεια, σε ένα ευέλικτο σύστημα, να αποταμιεύουμε ενέργεια και αυτό να δίνει νερό και ρεύμα στα νησιά, αλλά μπορεί και να τροφοδοτήσει και παραπλέοντα πλοία. Επίσης, επειδή υπάρχει υποδομή και ασχολούμαστε και με άλλα θέματα που σχετίζονται με την αειφορία, εργαζόμαστε και στον τομέα των ιχθυοκαλλιεργειών για την τροφή, άρα ώστε οι ιχθυοκαλλιέργειες να βγουν από τους κλειστούς κόλπους και να μπορούν να λειτουργήσουν και στην ανοιχτή θάλασσα. Εφόσον έχεις αυτή την υποδομή, μπορείς να ταΐσεις τα ψάρια, να τα παρακολουθείς και να μειώσεις το κόστος που σχετίζεται με την απομάκρυνση από τις ακτές. Άρα είναι ένα σύνθετο έργο που έχουμε πολλές ομάδες με διαφορετικές ειδικότητες. Έχουμε σημαντική συμμετοχή και από την κοινότητα και από το Δήμο Χίου και το Δήμο Ινουσών και το δίκτυο Δάφνη που εργάζεται, αλλά και από όλη την Ευρώπη. Άρα ο σκοπός είναι να συνδυάσουν πολλές τεχνολογίες σε έναν ευέλικτο τρόπο και να έχουμε μια καλή περιβαλλοντική λύση. Βασιζόμαστε στην ιδρυάδα που φτιάξαμε με επικεφαλή στο Πανεπιστήμιο Αιγαίου. Πάλι είχαμε αρκετούς φορείς που συνεργάστηκαν για να υλοποιηθεί αυτό το έργο, που λειτουργεί αυτόνομα η ανεμογεννήτρια και παράγει πόσιμο νερό. Λειτουργήσε σε αυτόνομα, με ανανεώσιμες πηγές ενέργειας, αυτοματοποιημένα. Άρα έχουμε ένα σύστημα που αποδείχτηκε ότι δουλεύει καλά. Και επίσης είναι ένα εργαστήριο που λειτουργήσε σε πραγματικές συνθήκες, παρακολουθώντας περιβαλλοντικές παραμέτρους σε σχέση με τον άνεμο, την παραγωγή της ενέργειας, του νερού και μετράγαμε και τη συμπεριφορά του ώστε να σχεδιάσουμε και να κατασκευάσουμε τώρα, είμαστε στη φάση κατασκευής, ένα μεγαλύτερο σύστημα που να μπορεί να έχει περισσότερες δυνατότητες. Εργαστήκαμε με αρκετές μεθοδολογίες πώς να συνδυάσουμε όλα αυτά τα συστήματα σε μια πλατφόρμα και που επίσης μπορούμε να τοποθετήσουμε τέτοια συστήματα. Άρα έχουμε να συνδυάσουμε διαφορετικές ανανεώσιμες πηγές ενέργειας και να αξιοποιήσουμε αυτή την ενέργεια και για παραγωγή νερού, αλλά και παραγωγή ηλεκτρισμού. Επίσης, μπορούν στο μέλλον να εγκατασταθούν και οι μονάδες που παράγουν υδρογόνο. Και επίσης, έχουμε συζητήσει και με άλλες τεχνολογίες που μπορούν να πάρουν το διοξίδιο από ένα πετρελαϊκό σταθμό, για παράδειγμα, το αρμόλιπο, το εμπλουτισμένο σε αλάτι νερό και να παράγουν βιομηχανική σόδα. Μια διαδικασία που είναι πάλι ερευνητική, αλλά είναι αρκετά ενδιαφέρουσα. Άρα για αυτό που δίνουμε έμφαση είναι η κατασκευή να είναι modular, ώστε να μπορούμε να συνδυάσουμε διαφορετικές τεχνολογίες σε ένα σύστημα και να αποταμιεύουμε ενέργεια. Αυτό που είδαμε είναι ότι υπάρχουν αρκετές περιοχές στην Ελλάδα που είναι κατάλληλες για την ανάπτυξη τέτοιων συστημάτων που μπορούν να δώσουν και ενέργεια και νερό και να υποστηρίξουν και την ναυτιλία. Άρα έχουμε ένα σύστημα που είναι αρκετά ευέλικτο, που μπορεί να αξιοποιηθεί σε διάφορες περιοχές. Σε πρώτη φάση εμείς σκεφτόμαστε ότι μπορεί να δώσει λύση στα νησιά, που σε πολλά από αυτά λειτουργούν πετρελαϊκοί σταθμοί και να λύσει σημαντικά προβλήματα. Και στη συνέχεια να υποστηρίξει και την ναυτιλία όταν εξελιχθεί και η τεχνολογία. Ευχαριστώ για την προσοχή σας.
Thank you very much to each and every one of our panelists for their excellent presentations. They were very detailed, but very concise, and we really appreciate them. Before I open the floor to the general questions and answers, I'm using my status as the panel chairman to make a few comments and questions to each of our panelists. To Stamati, I'll make a comment that also being involved in this incredibly complex regulatory process, I think, Stamati, that you managed to break it down into very understandable and easy to understand modules, because quite frankly, if one follows all of the detailed discussions, it's incredibly complex. However, you're absolutely right that we have to make sure that our short-term measures work, that our, in a certain way, our imperfect metrics that Panos talked about will help us to get to the decarbonization roles. And when IMO starts talking about medium and long-term measures, that our industry is there with your help for pragmatic solutions. Pano, I couldn't agree with you more in all of your comments. I am a great believer, especially for large and power-hungry vessels, on the concept of nuclear power. However, I think that what we often forget is that a nuclear reactor needs a boiler, it needs a turbine, it needs ways of converting the nuclear energy into propulsion. And I believe that we're going to need a whole new generation of engineers. If you look at what the LNG carrier industry has done, they've done their utmost to get rid of the steam engineers. And I think that one of the moves within the LNG carrier industry to diesels and diesel electric has been because of the lack of suitable seafarers. But I think that if we do go to nuclear, and I think that nuclear will be an excellent solution for many large vessels, I think that we have to, in parallel, look at retraining or upscaling the training of our seafarers, and also looking at the other parts of the system aside from the reactor. I don't know if you. Yeah, Bill, thank you. You have really opened our eyes to the real potential of the drop-in biofuels. A question is, at the moment, we burn a fuel which nobody else wants. The low sulfur fuel oil, high viscosity, is a fuel which cannot be used by trucking or aviation or any other sector really, except for power generation in certain countries. Is there a grade of biofuel which would be more easily handled within the shipping industry, which would be economically more feasible for us to take at an earlier stage than would be the case for other industries, so that it would be economically much more effective for us to burn this, if I call it a heavier grade of cheaper biofuel, which would not be suitable for SAFs, sustainable aviation fuel, or for automotive fuel. Would there be such a grade?
So far, we don't have a version like this. Of course, together with the price tag, we need to consider at the same time the carbon factor, because it's all about sustainability. And you have to multiply the carbon factor with the consumption to get at least the CO2. The aviation started using biofuels before our industry, but according to the fuel suppliers, it's easier for biofuels to scale up to our industry instead. So we may have a small advantage in this respect. The good thing is that it's the closest thing with what we're using today. Just to say some things on the positive side, there are no issues with toxicity. The flash point is even higher than the normal VLSFOs or high sulfur fuel oils. But again, it's a matter of supply and demand. I mean, before 2020, we were discussing about the availability of compliant fuels. And at that time, we were telling that, look, the refineries are not subject to MARPOL Annex 6, but the vessels are subject to MARPOL Annex 6. So it's a matter of demand on supply. The latest study was that biofuels with the current mode, they can supply up to 30% of the total fleet biofuels. But we don't have a cheaper alternative for the time. So the prices you've seen, maybe they were on the last slide. The Singapore B24 has a price of about $800 per metric ton. The B30 is about 900 in the Netherlands. would they continue to subsidize both the production and the transportation of biofuels? And if you really want to go crazy, it's B100, that is $1,775 per metric ton, but with a carbon factor of 0.7. So
Thank you very much, Bill. And Professor Lyridis on carbon capture. Of course, one of the concerns at the moment is the very, very high amount of energy we need to run the carbon capture system. There's been some research, and in fact, I think there's some pilot plants being built where a different process will be used by which a sort of type of carbonate will be produced, in which case there won't be the case of having to liquefy the CO2 and having to store it in special tanks on board, but we will have either a liquid like a slurry or even a solid component which would incorporate the CO2. And in this respect, I hate to be controversial, but in our regulatory point of view, we may have to talk about first carbon capture by itself, looking at the existing fleet, then looking at carbon capture and storage, and finally looking at carbon capture, storage, and utilization. But Professor, can you quickly tell us about maybe the lower energy processes which are starting to emerge? Thank you.
I think the most promising for the time being are the chemical processes. They do need some energy, but they are the most readily applicable. I think another way to see it, which is very important, is to use CO2 to produce some fuel, for example, methanol. In this case, over the life cycle of the production, you might prove that it is a carbon-free process. But still, that also needs a lot of energy. I don't think there is a golden section somewhere that you can actually capture CO2 and use it or store it in a very efficient way for the time being. Research is being made, and there are also small applications, and I know also some engine manufacturers also work on this. But for the time being, the most promising technology is the amine, the chemical process. This will give some temporary use of CO2, but for the time being, that's it. I think it is a big problem. Very expensive, basically.
Thank you very much. And finally, thank you to Professor Lilas. I think some very, very exciting developments on the floating offshore platforms. I hope that because these projects involve, unfortunately, a lot of land-borne bureaucracy, that we will be able to, let's say, upscale these projects to the extent that we need. I think that some of the technologies are applicable to shipping. Unfortunately, our vessels have the cargo handling component, which makes the technologies more difficult to apply directly onto vessels. But certainly, we will benefit from the green electricity in the form of cold ironing. And I'm hoping that land-borne bureaucracy will not slow down the progress of what you have talked about. Thank you very much. We've run out of time, but if there are a few questions, maybe we can take maybe 2 or 3 questions. Thank you. Dr. Pateras.
I just wanted to point out something, a couple of things, especially on the presentation by Panos. EEXI has affected all container ships. You said that it conveniently, we lobbied against it. We all have an EEXI certificate now and have a great reduction in our power, available power. but your pollutant graph, which came out at the size of the fleet in comparison to the production of CO2 or pollutants, is a little bit skewed because commercially, container ships are far more efficient than bulk carriers. And we spend our time in container ships transporting cargo and not sitting in port discharging cargo. So one way to reduce the carbon footprint of bulk carriers is put all the cargo into containers, and that would make it far more efficient and produce much less CO2. One other point is, the second point is, I agree with Dr. Fafalius that he says that there are a lot of carbon capture projects, and there's this new project in actually being done currently in Perama, with a conversion, basically the conversion is simple chemistry, CO2 to CO3, a carbonate, which is not a pollutant, which will be far more efficient by plasma. I can't remember the word now, but you're all familiar with this, and I think this is the way forward. All the other fuels that we're talking about are very, methanol, ammonia. We will have to change all our engineers. We know that. But for me, until we get to nuclear, which is the only way forward, we're going to go hydrogen. Thank you very much, Dr. Fafalius. And congratulations.
Thank you, Doctor. I will allow Panos to reply because he's very passionate about this.
Okay, maybe my words were taken out of context. What I meant is that the bulk carriers have been unfairly hit by those regulations compared to container ships, and also for CII. Since 2008, IMO has calculated how much each shipping sector has reduced its emissions so they can fix the targets for CII. And in 2019, the bulk carriers already had reduced their emissions by 40%, the carbon intensity. The containers only 28%. So bulk carriers had satisfied the 2030 IMO, but containers hadn't. Yet, the CII requires a 2% reduction per year in carbon intensity for all ships, the same for a bulk carrier and the same for a container ship. Now, it is a lot easier for a container ship to achieve a 2% reduction in CII by reducing its speed a little bit. It's a lot more difficult for slow speed ships. So there is an unfairness in that. They didn't want to look into the different sectors, what they have achieved, and lighten the requirements for bulk carriers. They put everything in one bag, and I find this unfair. I mean, that's the main thing. And another thing is, I mean, we have to admit the container ships are the major polluters, especially the big ones. There was a study from the National Technical University, the 700 biggest container ships emit more CO2 than all the tanker fleet, a lot more CO2. So this is what I was trying to talk about. Yeah. I mean, 700 container ships, 3,000 tankers, including VLCCs and all that. The 700 container ships that were the biggest ones emit more CO2. No. Oh, yeah, of course.
One more question.
It's not really a question, but isn't it down to the fact that container ships have a very much higher speed than the average tanker or the average bulk carrier? And we know very well how consumption increases, and that, of course, will create emissions. It's not
exactly
something to debate.
Exactly. It's a lot easier for them. It's a lot easier for them to slow down a couple of knots, and it's practically impossible for a bulk carrier to slow down a couple of knots.
I would say that technically, what you are saying is, of course, correct. Commercially, the lobby of cargo owners compared to the lobby of ship owners has a huge difference of scale. So I think that this is what it boils down to.
Ladies and gentlemen, time has dominated our proceedings. We thank you very much indeed. We thank our panelists. And again, many thanks to the university and the organizers. Thank you very much. Thank you, gentlemen.